Hello, friends. I'm going to do an example that'll help you use the equations. I hope you find it simple. Don't overthink it. Now, remember, you cannot use V equals F lambda. For a massive particle, meaning a particle with mass, when I say massive, I don't mean big. Maybe I'll just say particle with mass. Right? V equals F lambda is the phase velocity, and that does not work. So what do? You have to do kinetic energy is 1/2 mv squared. That's great. P equals mv. Kinetic energy is also h bar omega, and momentum is also h bar k, right? But you have to go through these, right, to get to velocity. So, and remember, k is lambda over 2 pi. H bar is 1.05457 times 10 to the negative 34, et cetera, et cetera. So if given velocity, say you're given velocity of like 100 meters per second for an electron, which is slow. Electron has a mass of 9.11 times 10 to the negative 31 kilograms. What do? You can solve for its kinetic energy, equaling 1/2 mv squared. You can then set that equal to h bar omega to solve for omega. Great. You can use P equals mv to solve for its momentum, set that equal to h bar k to solve for k. Great. You can also set mv. You can go now one of a couple routes. You can set mv equal to h over lambda, because remember, P is just h over lambda, and you can solve for lambda. Or you can use k is 2 pi over lambda, and you can solve for lambda, right? Right? So the point is you can get omega, you can get k, you can get lambda, you can get kinetic energy, you can get momentum. You can get everything. And now if momentum is known, that means position is impossible to know. See the last video. Impossible to know. So the fact that we say we know that this is given no longer can be an assumption about a particle, right? So I say, oh, the car is going 10 miles an hour. No, it's not. It's a 10 plus or minus, right? So we'd have to say, really, the momentum is 100 meters per second times the mass of the electron, right? Plus or minus some delta P, and that delta P is the unknown. It's like error bars. So that the X is like, oh, it's at 2 meters from the lamppost, right? Plus or minus some delta X, and delta X times delta P has to be greater than or equal to h bar over 2. Now it can be much greater than. I was doing some examples where it's much greater than, but it can't be less than that. So if, though, P is known, X is impossible to know, so we realize that that's an impossible situation. But if we did, then we could model this as x psi of xt, and it could just be a sine wave of kx minus omega t, where you just plug in k and omega from here down there. Now, that is physically impossible, but mathematically correct. I could do that. That's a wave function where x is impossible to know, but p is known. So if this is 100% accurate, this would be the wave function for that particle. Part 2, pause that. You can rewind it. It's a good one. Part 2. This is one we're going to do in class. Might do the other one in class. I don't know. This one definitely we're going to do in class, or have done, past, present, future. Let's say we know the wavelength is 10 picometers, and this is used in electron microscopes. They actually get down to 1 picometer. And I'll show you what electron microscopes can do. Their wavelengths are really tiny, which allow them to see more tiny things. Their wavelength is their resolution around. The resolution's a little bigger than their wavelength, but the smaller the wavelength, the smaller it can see. So that's why electron microscopes are better than light microscopes, because this would be a gamma ray if it were light. That's not going to work, right? So light microscopes, you get down to 380 nanometers, 500 nanometers, right? Maximum resolution. But for electron microscopes, you can get a little better, right? So the electron microscope, say down to 10 picometers, what is its velocity and what is its energy? The equations will get you there. So the velocity, you do momentum is h over lambda. Sometimes you don't need h bar. 6.626 times 10 to the negative 34 over 10 times 10 to the negative 12. Pause the video. Why did I do this? You can figure it out. It's easy. It's picometers, right? So that's going to equal 10 to the negative 11 down there, which is 6.626 times 10 to the negative, let's see, 34 plus 11 is 23 kilograms meters per second. That's kilograms meters per second. That's a tiny amount of momentum. It's an electron. So if I set that equal to mv, right, I get v is 6.626 times 10 to the negative 23, the momentum, over the mass, which is 9.11 times 10 to the negative 31 kilograms. If I plug that in here, I get the velocity of 7.27 times 10 to the 7 meters per second, which is about 25% the speed of light. And you might say, wait, doesn't that mean we need to take relativity into account? Yes, we technically do, but this is close enough to show us that for electron microscopes, we're now at the border of relativity. But this gets close enough. The real answer is close enough to this. At 25% the speed of light, you can still use these formulas. Any faster than that, you're definitely going to need to use relativity formulas. But close enough for 1 FMV squared, why not? It's close enough, let's do it. So you get 1/2 times 9.11 times 10 to the negative 31 times 7.27 times 10 to the 7 squared. And you get something, let's see if I can do it on my calculator. Or you can do p squared over 2m. Isn't that cool? You can do this squared. 2m, you'll get the same answer. Let's see what we get. I'm going to do 1/2 9.11 times 7.27 squared. I like doing it by coefficients. So I get 2.4 times 10 to the negative 31 plus 14 is negative 17. And I get 2 more, so I think times negative 15 joules. You can check my work, but that's what I got. Negative 31, negative 17. I got 2 more here, negative 15 joules. So I got 240 when I multiply all that together. That's your answer. That's it. Those are the types of questions we can do. These are the types of questions you need to know for electron microscopes if you design one. So this is where it starts to get real. That the electron wave nature allows us to see very tiny things. And I'll show you some cool pictures of how this is used in real life in class. That wouldn't be the case if electrons didn't have wave behavior. Have a beautiful day.